Imagine a computer so powerful that it could solve problems in minutes. These problems would take classical computers thousands of years. This is not science fiction. This is the promise of quantum computing. Quantum computing is a fundamentally different approach to computation. It harnesses the mind-bending laws of quantum mechanics. This technology has the potential to revolutionize countless industries. These include medicine, material science, and artificial intelligence. The quantum computing revolution is still in its early stages. However, the rapid pace of progress is astonishing. Scientists and engineers around the world are racing to build these powerful machines. They are working to unlock their full potential. It is an exciting time to delve into this groundbreaking field. Understanding quantum computing is becoming increasingly important. This is true for anyone who wants to stay ahead of the technological curve. This essay will provide a glimpse into this fascinating world. We will explore its basic principles, potential applications, and the challenges that lie ahead. The idea of quantum computing emerged from the early days of quantum mechanics. In the early 20th century, physicists were grappling with the strange behavior of the microscopic world. They discovered that the laws of classical physics break down at the atomic and subatomic levels. This led to the development of quantum mechanics, a revolutionary theory that describes the behavior of matter and energy at the smallest scales. One of the pioneers of quantum mechanics was the renowned physicist Richard Feynman. In the 1980s, Feynman proposed that the bizarre rules governing the quantum world could be harnessed to build a new kind of computer. A computer that could vastly outperform classical computers in certain tasks. This marked the birth of quantum computing as a theoretical concept. Since then, the field has attracted some of the brightest minds in physics and computer science. Key figures like David Deutsch, Peter Shor, and Love Grover have made groundbreaking contributions. These contributions include developing the first quantum algorithms and laying the theoretical foundations for quantum computation. At the heart of a quantum computer lies the qubit. Qubits are the quantum equivalent of bits. Bits are the zeros and ones that classical computers use to represent information. However, qubits possess a remarkable property that sets them apart: superposition. Unlike a classical bits, which can only be either a 0 or a 1, a qubit can exist in a superposition of both states simultaneously. This strange phenomenon arises from the principles of quantum mechanics. These principles govern the behavior of particles at the atomic and subatomic levels. Superposition allows a single qubit to store and process information in a fundamentally different way than a classical bit. But the strangeness doesn't end there. Qubits can also exhibit another mind-boggling phenomenon called entanglement. Entanglement occurs when two or more qubits become linked in such a way that they share the same fate, even when separated by vast distances. Measuring the state of one entangled qubit instantly determines the state of the other, regardless of the distance between them. This interconnectedness is what Einstein famously referred to as spooky action at a distance. It is a key resource that enables quantum computers to perform computations in ways unimaginable for their classical counterparts. The concepts of superposition and entanglement can be challenging to grasp. They defy our everyday intuition about how the world works. To understand how these quantum phenomena power quantum computation, let's consider a simple analogy. A spinning coin. Imagine a coin spinning in the air. Before it lands, it is neither heads nor tails, but rather in a state of superposition, representing both possibilities simultaneously. This spinning coin is analogous to a qubit in superposition. Now, imagine two coins spinning in perfect synchronization, their fates intertwined. If one lands on heads, the other also lands on heads. If one lands on tails, so does the other. This is similar to entanglement. The two coins, like entangled qubits, share a connected fate even when physically separated. A quantum computer leverages these quantum phenomena to perform computations. It manipulates and entangles qubits in a controlled manner. This allows it to explore a vast space of possibilities simultaneously. This is unlike a classical computer, which explores each possibility one at a time. This parallelism is what gives quantum computers the potential to outperform classical computers in certain tasks. Section 5. A world transformed from medicine to materials. The potential applications of quantum computing span a vast array of fields. Its impact on our world is poised to be nothing short of transformative. Drug discovery and development. Quantum computers could revolutionize drug development. They could simulate the behavior of molecules with unprecedented accuracy. This would allow scientists to design more effective drugs with fewer side effects, and it could accelerate the discovery of new treatments for diseases like cancer and Alzheimer's. Materials. Science, quantum simulations could lead to the development of new materials with extraordinary properties. Imagine lighter and stronger materials for aerospace applications or more efficient solar cells for renewable energy. Artificial intelligence, quantum computing could unlock new frontiers in AI. It could lead to the development of more powerful machine learning algorithms. These algorithms could analyze vast data sets and solve complex problems that are currently intractable for classical computers. Cybersecurity. The advent of quantum computing poses a significant threat to current encryption methods. However, it also offers a solution. Quantum cryptography promises to provide unbreakable encryption methods. These methods could safeguard sensitive data in a post-quantum world. While the potential of quantum computing is undeniable, several challenges remain before it can reach its full potential. Qubits are extremely fragile and susceptible to noise from their environment. This noise can introduce errors into calculations. Building quantum computers with low error rates is a major engineering challenge. Quantum computers need to operate at extremely low temperatures. These temperatures are close to absolute zero. This is to minimize thermal noise that can disrupt the delicate quantum states of qubits. Maintaining these cryogenic temperatures adds to the complexity and cost of building and operating these machines. Building large-scale quantum computers with a sufficient number of qubits to tackle real-world problems is a daunting task. As the number of qubits increases, so does the complexity of controlling and entangling them. Despite these challenges, the field of quantum computing is advancing at a rapid pace. Researchers are constantly developing new techniques to overcome these obstacles. As progress continues, we can expect to see significant breakthroughs in the coming years. The race to build practical quantum computers has attracted significant investments from tech giants and governments worldwide. IBM, a pioneer in quantum computing, has been at the forefront of developing superconducting qubit technology. IBM has made significant strides in building quantum computers with increasing qubit counts and improving error rates. It also offers cloud-based access to its quantum computers, allowing researchers and developers to experiment with this transformative technology. Google, another major player in the field, has achieved a significant milestone with its Sycamore processor. In 2019, Google claimed to have achieved quantum supremacy. This is the point at which a quantum computer can perform a task that is practically impossible for any classical computer to perform in a reasonable time frame. Microsoft is pursuing a different approach to quantum computing with its topological qubit technology. Topological qubits are theoretically more resistant to errors than other types of qubits. This could offer a path to building more robust and scalable quantum computers. These are just a few examples of the many companies and research institutions that are pushing the boundaries of quantum computing. The competition and collaboration in this field are driving rapid innovation. This is paving the way for a future where quantum computers will revolutionize various industries. It is important to note that quantum computers are not meant to replace classical computers. Instead, they are expected to complement them. Classical computers excel at a wide range of tasks. These tasks include browsing the internet, word processing, and running most of the software we use daily. Quantum computers, on the other hand, are particularly well suited for tackling specific types of problems. These problems involve complex calculations and simulations that are intractable for even the most powerful classical computers. The future of computing is likely to involve a hybrid approach. Classical computers will continue to handle everyday tasks, while quantum computers will be used to solve specialized problems in fields like drug discovery, materials science, and cryptography. This collaborative approach will harness the strengths of both types of computing to address some of the world's most challenging problems. The quantum computing revolution is still in its early stages, but the future is brimming with possibilities. As we continue to unlock the potential of this transformative technology, we can expect to see profound changes in the way we live, work, and interact with the world around us. Now is the time to delve into this fascinating field and explore the endless possibilities it holds. Learning about quantum computing is no longer limited to physicists and computer scientists. Numerous online courses, tutorials, and resources are available for anyone interested in exploring this groundbreaking technology. One way to start your quantum journey is by learning a quantum programming language, such as Qiskit or Cirq. These languages allow you to write code that can be executed on real quantum computers. By experimenting with quantum algorithms and exploring the principles of quantum computation, you can gain a deeper understanding of this revolutionary field and contribute to shaping the future of technology.